Two here. Hey, welcome to Coffee Compiler Club. We're here today to talk about compilers and language runtimes. And here's my shirt I'm wearing. It's finally warmed up enough. And languages and garbage collection and typing systems. And what are best practices for writing compilers versus sort of standard industry best practices when you're doing, I don't know, web apps for doing storefronts or whatever. I think they're going to be very different things. So that's, we're already recorded. You'll be on YouTube in a couple hours. That's the starting spiel done. I guess I was just talking with Cameron, although Cameron, you are muted maybe, that about best practices for compilers and language runtimes and the like, and when to pick up dependencies and why, and how you test some things. And I was complaining about testing. There's no good testing support for testing concurrent projects, and specifically language runtimes that support concurrency. The sort of standard industry testing harnesses typically don't test, or they just get in your way.
I mean, also, it's usually you don't have like existing recommendations because you're trying to build something new or different with your language. So you're disregarding lots of advice from existing languages because you're explicitly trying to be different. So
explicitly being different, yes, there's that one too. So one of the fun bugs in the JVM versus JUnit and concurrency testing is that your test spawns threads and then wants to wait for them collect their answers, and one of the threads throws an exception, and no one catches it because that thread's not supposed to throw an exception. Then it's thrown away. When you join against the thread, the exception is gone. So the very act of using like JUnit to test something means that your test that throws an exception in an off thread will simply pass as no exception. As a for instance of an easy, quick way that the testing harnesses were like actually getting in the way. Fine. That Cameron is nodding sagely. Did you want to add anything there?
It's all about braces placement.
Yes,
Hey.
Cameron, I have strong disagreement on braces.
There's like the correct way in the way Microsoft does it, right?
Oh, I see. Wait, Microsoft did it right?
No, the other way around. The correct way and the way Microsoft does it.
Got it. Okay, good. You didn't say anything about Clifford normal form. That's the way Clifford does it.
Yeah, the two spaces thing I've used before. I used to be much more fond of it, but I gave up on that one.
Okay, 2, 3, and 4 seem to be an industry standard. One of 2, 3, or 4.
Yeah, usually you want to pick one of those.
Yeah, and then the Linux guys do tabs, and everyone gets to pick 2, 3, or 4 themselves personally, but they must use a tab to do an indent so that everyone else's indentation is correct, whether they've picked 2, 3, or 4.
Yeah, I never understood that because it doesn't really work that way in reality.
Yes.
And then it just looks like shit unless you're all using the exact same tab. It's
Yes.
like,
Well, isn't the answer that the answer is I don't care because it's done automatically by Git-hook in the repository that runs the formatter? And if the formatter inserts tabs, then the tabs they are. I mean, who cares?
I've also used automatic reformatting with every Git input, and maybe it's better now, but back when I did it, whitespace turds from the it wasn't a bijection. So every time you went in and out, you got a different whitespace turd that was part of the diff that went back in with your diff. And so you endlessly got stupid diffs.
No.
wait, you're not using Windows, are you, Cliff?
This was on Linux, sir. You can't hammer Windows for this one.
Because I used to have to deal with people putting those
Character line fees?
ASCII 13 in all over the place. Like,
Yes.
what the fuck?
Yeah.
You didn't even change anything.
Cameron,
You
how
just-
can you, if you don't return the carriage, how can the typewriter start writing the new line?
Exactly. No, I mean,
It just runs down the 80-column margin
so
indefinitely.
just so you know, Matt, new line was used to
Exactly.
advance one line. So
It's vertical. Yeah.
it went vertically. It just didn't go back to the left.
Yeah, it required 2 steps.
Don't you know anything about TTY?
I use those stupid machines. I coded on them. What the hell? Fine. No,
There,
that
there
one
used to be games on them, which was funny, especially when you had to
yes.
have a full screen redraw. Because
I did games on those.
that was you.
That was me. Yeah, fine. That one never bugged me in the in and out bijection because I had just said always remove, and then the Windows guys got them, and then the window put back removed, and that was fine. And then but it was the other one where you fiddle spaces in and out and braces in and out, and I do a lot of vertical alignment on purpose to get vertical coding to show off the differences because they're aligned vertically. And as soon as I have an auto indenter come along, or auto formatter, he's confused by vertical indentation and blows it away or something. So I have to fight that. But even when I was just doing a standard project with a bunch of guys doing whatever way back in the day, Linux, blah, blah, blah. You got white space turds on every push and pop because it was not a bijection. All right, done with white space turds. What else?
Okay, so my take on the best practices was like, what's the best way to structure compile? So like, you know, there's like the nanopass stuff where like you write lots of little passes, and then there's the, I mean, I think some people, you know, they're like opposite. They say, you know, single pass for a compiler, you know, make it
Not to
fast.
mention me or anything, but yeah. So like there's a history where passes were added one at a time, and LLVM just went straight down that path, which is all fine. That was a historical, when I was growing up and went by many, many compilers, historically, there was a parser possibly broken into 2 or 3 passes, including, you know, type checking and lexing and whatever. There was a middle end, which did something, and again, passes were added because it was the easy way to do it. And there was a back end, which was probably a couple passes as well. And so yes, pass after pass after pass. And the nano guys were like, fuck it, all these passes have all identical sort of overall structures, and inside the middle, they do a little different things. But we can pull out the structure that says for all everything, go visit. And that was sort of the start of the nanopass concept. And then we can shuffle the passes around and whatever, except you can't really shuffle the passes around because you have to, you know, register allocate toward the end of things no matter what you do. You have to parse before anything else and blah, blah, blah. So that only went some distance.
I think it's also a matter of maintainability. I mean, I think the selling point of nanopass compilers is that you can write tiny passes that do exactly one simple thing, and it's easy to test before and after. And I think the only thing that's limiting, or that has always limited nanopass compilers, is the compiler technology to fold these 120 nanopasses into like 3 or 4 real passes, so that you get to write things as if it were a nanopass compiler, but get the performance of a real compiler with real faces, I think.
Right, there's 2 performance issues here. One is how fast is the 120 passes, and I want them folded into 3, right? The other one is how performant is the generated code, because the passes all have dependencies afterwards on each other, and you want to have some way to say, having run in the loop invariant code motion, I need to now stare at my loop to see if it needs to be unrolled or if it's small enough or whatever. Having run common sub-expression elimination, I've now discovered a constant controlling an if test, and I want to fold the if to get some dead code, and then I get more constants, and around you go. So integrating those so that their results give you the result of a single sparse conditional constant propagation pass, for instance, which is a fairly subtly thing, is difficult. Oh, and here is Aaron even. Another.
So I ended up doing a hybrid of nanopass and C nodes, because I have this thing where I'm compiling from Python, and then I do a bunch of initial translation and dependency resolution stuff as nanopass. So they're all a bunch of really small passes. I'm not trying to fold them into separate things. And the IR for each pass evolves. So I have a little dialect that I created that tells me how the IR diffs between passes. And each nanopass is just maybe 10, 20 lines of code make the specific changes. So it's kind of tight in the same way that the rules for the sea of nodes is. It's a predefined order, and I have no illusion that I'm going to be changing the order of these passes. It's just a simple process going from Python to my sort of IR that I then ingest into the graph, and then I do graph passes.
Yeah.
And I really like this. Well, I think it works quite well because nanopass is quite nice for simple tree structured edits.
You don't have such a speed issue that you feel driven to fold the passes.
That's right, yeah. And actually I was doing some profiling for the first time ever on this project, and I thought that my passes and the graph rules were the majority of my time, because it does a lot of rule matching. A lot of it's really redundant, and I just decided, well, I'll leave it for later. So every node that I run, every node in the graph gets checked against every rule every time. So
Okay.
Right. So it's like not, there's some obvious optimizations that could be done there. But when I profiled it, I realized that actually that stuff didn't even show up in the profile. It was other stuff that was taking all the time. And the biggest thing was actually building the Python AST by far.
Using Python, right?
Yeah, it's using a Python library. And in fact, it only uses one built-in Python library, just gives me the AST. I walk it once into a data structure, and then I'm done with Python forever. But that's still like 1/3 of my total compile time.
Yeah,
So,
okay, yeah, fine, ouch. But Python, what are you gonna do?
Yeah.
Yeah, H2O had a Python wrapper library that would take Python simple expressions and forward everything to build a URL, and hand it off to the H2O cluster as a URL to go compute an answer and come back with. And but we didn't do like large Python anything, so it didn't turn out to be too expensive. But we walked a Python AST basically, not with a library. We did overloads. We overloaded everybody to be a data frame, like a pandas data frame, except the act of executing the data frame was to walk it internally and build a URL, ship it off to the cluster, get the URL result back. A little different setup there, fine.
Yeah, I thought about doing it that way too, but I had some back in the old days, I was doing Ruby, and I had some success doing a very similar thing where I just grabbed the Ruby AST and did some very simple sort of interpretation of it to do. And that worked so well. I thought, okay, I'm going to try that for this. I got my whole, sort of my first pass Python ingestion thing going in a weekend. So I was pretty happy.
Yeah.
It's really easy to write those passes.
Hey, so Arthur, we're talking about best practices for writing a compiler, and there are some complaints, or I added complaints about LLVM. Did you want to throw out anything about your experience with LLVM and how the pass structure works, or how much it's nice and what a better structure would be? We're talking how you design these things.
So I think in general, the pass structure and the pass manager, I think it's pretty good. I don't have specific complaints there. It has this it has this notion of analysis that are the pass manager keeps track of analysis and invalidates them and caches them. That's a nice thing, though. As usual, when you try to update or invalidate analysis, that's usually a place where bugs can hide. I don't know, you misinvalidated, you forgot to drop the analysis or something. But I don't know if there is a much better way to organize this. I think one alternative is to try and cache the results of your analysis in the IR, so as to make this update and invalidation more obvious when you modify the IR. And I think that's what C2 does with, for example, memory logic. But then you still have this issue. Okay, you can forget to update the graph properly.
That one's not typically happening for C2 or AA. There are other things that do screw up in there, but there's easy testing for that one. For me, at least, there's easy testing for that one. I have a hard, quick test that will point to the exact rule that failed to update.
Maybe if you have this tighter coupling between analysis and IR, maybe it's easier to have to just check stricter invariants about them. Like if you modify one, you have to modify the other. But then with this tight coupling, it gets harder to introduce new analysis this way. Like when your analysis is just something on the side, I don't know, literally a side table where you remember something. Right. It's just easier. You can like create them on the spot. You can like change them. When it's part of your IR, that's
I think you should try coding C2 performance improvements hacks before you come around, or AA at least, because AA is the cleaned up version of C2 in this sense. But before you head on that, I don't know LLVM other than you said there's a pass manager, and that was a red flag. Whoa, pass manager, holy shit. Whereas for AA, I know that I've added analyses and they don't cause other weird interactions. That's not an issue.
Like you still have something similar to pass manager. Like there is something that runs individual transformations and right.
So in the land of AA, because of weird typing games I'm playing, there's more than one pass over the IR where I flip a flag to go to round 2, but the flags I'm flipping are, you're already got a broken program, and now I am propagating the errors where previously I was pending the errors and letting it wait. But there's not, in the sea of nodes things, there's not any more passes. So now I'm not doing code yet. Now you go look at, passes in that way. I have a one-step parse to an IR. I got a one-step IR to typing internally, or after the one step for typing, there's 2 or 3 passes that propagate errors of different kinds. So I get an error out. If you don't have any errors, those passes are empty, do nothing. And then in a theory, in a future AA, there's going to be some passes to make code. And as a minimum, I probably have to do a loopy thing that's separately special. And then there'll be a graph layout to a control flow graph scheduler and an instruction selector and a register allocator as sort of passes, but those have strong ordering dependencies. There's going to be 1, 2, 3, but there's not any other analysis passes running around like they are in an LLVM style. Like I don't have separate dead code or loop invariant motion or common sub-expression. Those are all the same thing.
Well, wait, it's a big part of it is because it's just a part of scheduling the graph. Like you don't need to do explicit hoisting of invariants out of loop. It's just a part of scheduling.
Yeah, that one got disappeared for being the sea of nodes. So I'm looking for, in your head, what is an instance where I want to add an analysis and it's going to badly interact with the current state of analysis that I got out of, running the integrated people typing pass.
Well, I have one that I'm thinking about now, which is loop analysis.
Yeah, I said loop analysis would be a separate thing, but there's reason for it. But it's actually loop transformation is separate. The analysis I can pull out of the graph without having any weird interactions. Do you want to hear how that goes?
I would like to hear it, but I don't know if anyone else does.
So the first easy cut is that I'm going to ignore irreducible loops, in which case every loop has the property that there's a back edge and there's a go around edge, and all I have to do is number from the top. So in the land of C2, I built an incremental Dominator tree that I let get lazily out of whack, and it periodically, it was always at the loop ops, I would rebuild it. But it's good enough to guaranteed find all the back edges that lead into a merge point. So every merge point will look at his immediate Dominator, and one is above him and one is below him, and he's done. He's a loop edge. He's a loop back edge. At that point, I would flip him with the people into a special loop node, which just hardwired, had a bunch of extra analysis virtual calls tagged on them. But it was basically a bit flip. You're now a loop node. And
so you're saying a region node becomes a loop node?
Yes, a loop node inherits from region node, except the left edge, it has two edges. The left is the fallen, the right is the back. There's shortcuts, abbreviations to ask for the two different guys. Then there's a couple other things that you start doing with them that says, because I know I'm the head of a loop, I can do the following things about what I know. And then I start looking for like trip counters or induction variables. An induction variable is a phi node, which points to a region, which has the loop. Okay, and it has a fall-in value. That's the starting point. It has a back edge. And the back edge goes to an add of a constant. It's a +1, a blah, blah, blah. Suddenly, induction variables fall out of this as well. And I still haven't done any global analysis except incremental dominators, which I build in the parser. We build
so that's an example of how you can store the result of the analysis in the IR.
Yeah.
Like you literally rename a node and say this is a loop.
Yeah. Yeah.
In this case, what LLVM does, it keeps a site structure that describes the loop nests, and it just remembers, okay, these blocks they form a loop. And with the IR, you modify the IR, and more or less you get the update of the analysis for free. With LLVM approach, you need to, when modifying the IR, you also need to modify the site structure.
Right.
And
that was the point of doing it. What I did in the IR is I didn't have to modify the site structure. In particular, if in the course of more analysis, I discover a loop trips only once, which you discover because the back edge is dead. The test controlling the back edge goes dead. The loop goes dead. The region folds away, the loop node folds away, and I don't have to update a side structure saying I changed my loop structure. It just happened.
This is also similar to what MLIR-based compilers are going to do. In a sense, they take it even further because you go with this idea of progressive lowering, where you start with the highest level concept and then you only lower this as you need to. So say you have a machine learning model that does something on entire matrix. You do not lower this to a for loop.
Yeah.
You produce a linear algebra dialect operation that corresponds, for example, to matrix multiplication. Yeah. Then and only then, if you are ready and you have done all of the transformation, notice that you can already do transformation, say like matrix times matrix times matrix reordering, because you know it is easy to multiply the small matrices and keep them small as long as possible, and only at the end multiply by the larger matrix. Imagine doing this on a nest of for loops.
Yeah, right.
With scalars. That would be crazy. So of course you will do this on the linear algebra dialect. And only when you are done with the linear algebra optimizations, you are going to go to the structured control flow, which is in short SCF, which has the SCF for operations. That is going to encode the loop bounds. You can also have a find for, which guarantees that the indexing operations are affine functions of the induction variables of the loop, which makes certain transformations trivial. Say if you want to fuse one loop with another, you just invert the affine map, which maps the iteration space to the access space to give you access space to iteration space, composed with the map of the other loop, and then you have composed fused loop in one line of code. Yeah. When you are done with the affine operations, then you use the structure control flow, and at the very end, you lower to control flow dialect, which just has a branch statement and if and switch, which is pretty much what you start with when you have LLVM IR. So this is how low level LLVM IR is. It just starts pretty much with branches, which are at the very end of the dialect hierarchy in MLIR.
Hey man, let me interject a few meta things here. So then ask for the link into the Google Doc. That paper, by the way, is from 1990, which I don't know how appropriate it is. Maybe, maybe not. And what was I going to say? Stupidly, C2 has the affine version of a loop, goes to a counted loop, which has known affine bounds can be gotten with, but I don't do the trivial collapsing folding in the one line because at that point I'm a loop nest. And so yes, it's too late. So you're correct. You won't do that in high level. And wait, and then Levo, you raised your hand. Did you intend to ask a question?
Yeah, I'm not sure how to ask this question, but you're just talking about loop domination and a few other things. I was just wondering,
Dominator tree.
Do you have a way to make between passes or during the seed of the nodes? Is there a way to know? Do you do something to make sure your data is like correct. You didn't like mess up your IR or your nodes or anything.
Yeah. So the usual story, this is a testing question. It's not incremental dominator. It's a testing question. So I run a test, something broke. Okay, what the hell happened? I turn on, go slow test mode. And in go slow test mode, after every minor peephole change, I revisit everybody in the graph and validate that they have certain properties. Their types are monotonically increasing. If they have a peephole rule that will fire, they're on the work list. And then internally, they have some other checks depending on what they are. Like if they can unify and the incremental unification, they're on the work list. Whatever. There's a number of things I can assert for. That one comes with a deterministic trip counter out of the work list. And when I fail that one somewhere, I read the trip counter, set the breakpoint, go again, and I stop before I'm about to do a transformation that when I'm done leaves a graph in a broken state. That's how I debug those things.
Okay, because I've done a couple of static asserts, and that sounds more interesting. Like what you just said, it sounds more interesting.
Yeah, the key with the peephole game is that it's always one peephole is the first one that left you in a broken state. And so you just have to find a way to find that one. And now you can stop and see, oh, I did X, I transformed X to Y to Z, and then something stupid, and wait, and go hunt around the graph and see why you're no longer correct. And it's all, peoples are all local, so there's some region you have to inspect manually to decide what was broken. But it's a relatively straightforward, generally, knock on plastic. Sometimes my asserts don't catch the breakage soon enough, and I have to roll backwards a ways. Wait, this guy's type is too weak. He got it because his prior component's type was too weak, and I have to roll backwards. Why are you too weak? And oh, somewhere way up here, you flipped from blah to blah to blah to blah. You forgot all knowledge you should have had, and fell to some bottom type, and and whatever. Sometimes it doesn't come so quick and easy. Most times it comes quick and easy. Sometimes I have to go backwards a ways.
I have something like that for my IR. And I just try to rule out a lot of states, and it makes things simple. But I have like a basic version of that in my IR.
There's a test manage for testability or change your code for testability, where if you have a series of processes you're going through, you want to maintain some counter or something that says I'm following through. Oh, I broke here. Now I can breakpoint before I hit the broken spot. There's like a pass manager where you got broken somewhere after the middle. So you binary search the passes, and then you're pretty certain that it breaks when I run this pass following it. And now I go in the debugger and start saying, what happened here? And why did this pass leave me broken? There's
one of the things that LLVM Pass Manager provide you, various instrumentation, like, I don't know, printing, or like having the bisect functionality where you just stop at some point.
Yeah. I have bisect by people rule as opposed to by pass, but conceptually that's the deal.
Yeah. For the Dominator, for the Dominator tree, you have this as a side structure, right?
Yeah, not in C2, no, it's in the nodes.
So in the nodes you have the edge that shows the Dominator.
Yeah,
like from
and I intend to do that in AA at some point. Yeah, and the transforms that do updates that would change it have to modify the Dominator, but almost always the updates are I deleted, and so the Dominator is just the Dominator of the parent, and that's folded into automatic delete a node guy. Oh, you have a Dominator notion. Oh, go ahead and patch the edge in the Dominator tree in a conservative way.
One downside of having the analysis in the IR is that everyone who does some kind of modification needs to know how to update and invalidate them.
Yeah, and right. So the two pieces of that for the incremental Dominator, that's such a normal, trivial hack that the default harness does it for all peoples for you. And then the other piece of that is the tester wants to test these invariants that the incremental Dominator is conservatively correct, for instance, so that when I go into my go slow, go test mode, if a peephole needs to do something other than just delete the edge in the Dominator tree and tighten the Dominator tree up, the tester will find it in one pass.
So when your analysis are not as tightly coupled with the IR, you have an option to say, well, I don't know what kind of analysis there are, but I just do not I invalidate unknown analysis.
and then you have to live without it or rebuild it.
Yeah.
And I go in the zone of, I have it always. Certainly in the case of both Hindley-Milner and the flow types, they are 100% correct at every step. But they monotonically move toward the final answer. And in that case, I can't live without those. That is, in fact, the output of the guy.
Yeah,
And the incremental dominator, he's just there to do efficient removal of various kinds of dead code.
Yeah, the Dominator tree analysis in LLVM is one of the analysis that's like in theory you can drop it, but in practice everyone preserves this just for compile time reasons. Like everyone needs it, everyone preserves it.
It's a handy thing. Yes.
Yeah.
Yes. In the land of Java bytecodes, you get repeated checks. Everybody checks for null. Everybody checks for this or that. It's repeated checks all throughout. If you got a Dominator tree, you can go up the Dominator tree very fast and find, oh, this has been checked earlier in life. I don't need to check it here. And that's where I get it. That's why I put it in for Java, at least. That there's just so many repeated checks, and it was so cheap and easy to get rid of them.
Yeah, we do the same.
Yeah. Okay. Yeah. And then Derek, you were trying to say something.
Oh yeah. Just going back a bit to like sort of how we trace for errors and stuff. And I do kind of the same thing as you. I mean, it's inspired by what you described, but I do it a different way, which is I snapshot my graph after every people. And so I have an immutable, like I have a data. Yeah. So I have
persistent
a
snapshots
data structure that I use that can yeah, fairly nearly free. And so I can switch it between being immutable and mutable. So when I'm inside the pass, the graph has already been switched to be mutable, so I can make changes. And then the sort of manager thing that's just sort of iterating through all of the peepholes and looking after deletions and all that stuff. After it's done, every peephole, it's snapshots and it creates a history structure. And so then I can create these sort of outputs of all the histories of a compilation.
Wow,
and I can also
sounds
just
like
go
it would
back.
Get big.
It hasn't been a problem so far, but the programs that I write that I'm doing are relatively small. So
because of the nature of what you're doing.
Yeah.
Interesting.
So it hasn't been a problem. I've never bumped my JVM past the 4 gig, and it's usually sitting there, not memory constrained in any way. So
doesn't care. Interesting. Yeah.
If your programs ever got too big, they wouldn't fit on the chip, though, right?
Exactly. Yeah,
So
but
you
the
have a
graph
sort of
gets
fundamental
a
ceiling.
lot bigger. It's especially so there's a lot of stuff that gets inserted into the graph, and especially because there are a lot of there's a lot of kind of stuff I have to keep track of speculatively because of the way that I have sort of 2 systems that are compiled together, the array and the controller. And there are a lot of things that, like, for instance, every time I do like an addition statement, I have to attach a pile of stuff to it that relates to state that could be in the array in case that addition is happening in the array. And then later on, as it sort of the types work out, it figures out, oh, this is in the risk controller, and it detaches all that stuff, or it's an array and it doesn't. So the graph ends up enormous, even for small programs at first, but it doesn't seem to be a problem for space. Problem for time.
C2 considered 100,000 nodes a big compilation, but because we're JIT-ting, we were willing but we wanted to keep it small, so we were willing to cut inlining off if we started getting too big. But that was sort of the translation from Java to IR, not PE array.
Yeah. And I've used this same, so I wrote this graph database, and then I adopted it and I used it for this thing. And before I was doing this, I was doing some analysis of other stuff where I had tens of millions or hundreds of millions of nodes, and it was fast to build a graph and fast to query. So it was pretty good, but it's still a lot slower than Cliff's method, which is like really good with cache locality and stuff. Mine has nothing about cache locality. What I was thinking of doing actually is, if I need to optimize, I will create an interface equivalent version that works like Cliff's, that then I have a fast way of compiling, and I can then switch back and forth between these. We'll see.
If you have to keep your program small, do you, in the language, do you like avoid templates and generics, and what do you use instead?
Yeah. Yeah, because I'm compiling from Python. So Python is my syntax, so there's no question of that. And in fact, not only that, I don't even let you define classes. I have a handful of predefined types of things that you can use, and you can instantiate them, and that's it. So it's a bit restricted.
Can I make my own arbitrary dictionary?
Yeah, you can.
Leva, what is the thumbs up? That's just a voting thing. I haven't ever done this thing. It's gone now. Fine. I don't know. Zoom hacks. Yes, there you go, Aaron. That's what I need to see. Okay, what else? Matt, did I cut you off? Yes, and there's Matt saying, woohoo. I don't even know where this thing is.
So Yorick finished his initial LLVM.
Oh yeah, Yorick, where are you?
I'm here.
He lives. Yes.
I guess I'm here. Yeah, no, I finished it, released it today. Yeah, I mean,
tied with Cameron there. Yeah, congratulations.
Where do I begin?
Braved the depths of LLVM and came back to tail the towel.
No, I mean, I think in hindsight, like LLVM is not that. I wouldn't say it was easy. Definitely wasn't. But it wasn't as daunting as I had imagined. I think the challenge here, it's a big library. There's a lot to learn. Kind of figuring out what certain instructions to generate. So, for example, if I think I mentioned it before, like if you want to do like I had an instruction where I wanted to check if a floating point is not a number. I think it was that one. I think I mentioned in the previous call, but I was like, do I have to generate this myself? Is there some sort of instruction or intrinsic for this? And yes, there is, but those kind of cases are a bit tricky to find. So then you basically have to look at the output of Clang to see, oh, what does Clang do? Oh, they use this thing. What's the documentation? Oh, okay, that makes sense. So there's, I think like any big library, there's the challenge of sort of connecting the pieces together. I think my biggest concern is going to be the distribution side of things, in the sense that LLVM's API is not really stable. I believe they don't follow any kind of semantic versioning, other than, generally between major versions, like inside, let's say, major version, things will keep working-ish. But so my concern there basically was like, oh, if I end up using, let's say, LLVM 15, which is what I'm currently using, is that going to be a problem? Like, is it not going to be widely available or whatever? But it turns out that basically most Linux distributions, at least, have accepted that LLVM doesn't really have a stable API across major versions. So there's just packages for every major version. So it's like LLVM 14, 15, 16, etc. It's a little more annoying on like a rolling release distros like Arch Linux, because there's a package called LLVM, which is whatever the latest version is they ship, which right now is 15. Whatever. Tomorrow that might be 16. Whatever. And Arch does have packages for older versions. They have like LLVM 14, I think, still in the main repos. But it means that, basically from one day to another, your installation instructions might no longer work. So now you have to, adjust those, maybe push a new release so your package depends on the right version. guess the summary there is I'm glad I'm no longer using Arch. I moved to Fedora, saved myself a lot of trouble. Yeah, and there are some minor things like I'm essentially using two libraries for interacting with LVM. There's a sort of quote unquote high level library called Inkwell. And then there's essentially these sort of raw Rust bindings provided by a library called LLVM sys. And Inkwell uses LLVM sys with the sys library, basically just being a Rust version of the C API. And there was the problem that the sys library, it only supported static linking against LLVM, which in general is what you want because of those version issues. The problem was that on Arch Linux, they stopped shipping static libraries with their LLVM package. And so people reported some bugs like, hey, this thing I was building with LLVM is no longer working. What the hell? And reading through the issue, the comments were kind of typical for like Linux users in general. Like, oh, that's not my problem. You have to just fix it here. This downstream thing is like, well,
it's working on my machine.
Oh, their argument was, I think, if I remember correctly, basically along the lines of like, oh, we don't need it, so it's your problem. It is the way it is. But then, unfortunately, somebody a while back submitted some patches to this library to also support dynamic linking. It wasn't released yet, but I poked the maintainer, and they were kind enough to release it a few days ago. Which means you can now use it also on Linux distros that don't ship static libraries. And then I think it picks it up automatically. So at build time, you can say, hey, do you want to prefer static, dynamic? Do you want to force one of them? So it's now set up to basically prefer static linking, but it will fall back to dynamic linking if needed. Then there's the thing where Alpine, I think this is more of a Rust problem where, if it says correctly, if you build a library on Alpine using Rust and you're linking against C libraries, then on Alpine or actually any muscle-based target, it won't apparently include the right directories as the library search paths. So it won't be able to statically link against the libraries because it won't find them.
I just want to interject that you're making me very happy that I'm using the JVM right now.
Well, so these things, they are annoying. And this particular bug is not solved yet. Last I checked, they're still working on it, but it's some weird test failures they're trying to figure out. To be fair, Alpine, I don't really care that much about. It's nice being able to build a fully static library by targeting the muscle libc. But on most Linux distributions, is not really a problem anyway, because glibc is widely available, and I'm not really doing anything that requires very specific versions of glibc. That's not like I'm using some latest function that's only available in 2 out of 20 distros. So it's it's annoying. That's not the biggest deal. And on macOS it just works fine. Like there's no problem there. I did end up dropping support for Windows. The sort of overarching story there is I'm not a Windows developer. I have a Windows desktop for playing video games, but I'm planning on replacing that with Linux somewhere in the next 1 or 2 years.
This sounds familiar, Cliff.
And so basically, my knowledge with developing on Windows is restricted to whatever I absolutely needed to know to get builds working in the past, which is very limited. And as part of these LLVM changes, I changed my runtime so that context switching between my lightweight processes is done using assembly. So it's basically as lightweight as you can get it. Instead of having to use like deprecated POSIX APIs and things like that. I say deprecated because they've been deprecated for like 20 years and they still exist.
Yeah, set context.
Yes.
Yeah. Did you lift the assembly from the boost stuff?
I pulled it. I looked at like 15 different sources and tried to like narrow it down to the smallest amount possible. Made it work.
x86, the boost stuff seemed pretty good when I looked at it.
I believe I used it as a source of inspiration. I believe it was a bit complicated because they had like a whole bunch of if-defs thrown in there. But yeah, eventually using different sources, I pieced it together for x86 and x86 64 and ARM64. I had most of it for Windows, but the problem I would run into is that in certain cases, it would just crap out in like random places. And the pattern was very indicative of memory corruptions. And my guess was that because perhaps my stack switching assembly was not done correctly, it would end up doing whatever the hell it was doing. Now, the problem here is in typical Windows fashion, the errors you get is just like access violation, 0x, big number. And you're like, thank you, that doesn't help me at all. And if you throw a debugger in, you also have no clue because it will just, like you run it 10 times, it services in 10 different places. So I spent quite a bit of time trying to figure that out. And eventually I was like, you know what? There's no people using this on Windows. I don't think people will be deploying this to Windows for the next 10 years, assuming they're going to deploy it anywhere in the next 5 years to begin with. That and some other things just making more complicated. So, you know, sorry, Windows people, but no. Bye. It's because it was not just a runtime. It was yeah, some stuff like the socket API where even though I was using a wrapper library, you still had to like deal some things where like in very certain cases, if you have like a non-blocking error thrown, or so like this would block in case of a non-blocking socket. Windows will then have like 2 different error codes instead of Linux. So you still need like special case, like, oh, on Windows, we also have to check against this status code. A bunch of stuff like that where, you know, if I was or knew somebody who was a, you know, Windows developer and was willing to commit, you know, a serious amount of time towards this, no problem. But yeah, I don't think I'll have that kind of person for at least many, many years. So I was like, no, I'm not going to delay this. Screw it.
So this is interesting, but I'm a little bit lost because I'm kind of curious what you're using LLVM for. Like, what are you actually doing with LLVM? Or maybe you've covered this and I should go find it there.
Oh yeah, sure. Yeah, so LLVM is my compiler's backend. My sort of long-term vision there is like, sorry, go ahead.
Do you have any of like your own passes or anything that you've written, or are you able to lean on the LLVM sort of as is without sort of having to modify it?
So right now I don't have any optimization passes like at all. My long-term vision there for the compiler is that I'm going to use LLVM as sort of a dumb code generator, in a sense that all the interesting optimizations I will do myself on my own IR, mainly so I can have a bit more control over how well it's going to perform in order to keep compile times as fast as.
What kind of optimizations are you doing that LLVM will not?
Right out, none.
Well, what are you planning on? What are you thinking?
Things like, well, LLVM does do inlining. I haven't figured out if it can do inlining across LLVM modules. I don't think so, because maybe Arthur knows more.
Should be
experience was no, but
yeah, it could be in one module for inlining to happen.
Okay.
Right.
It doesn't. So I tried.
Right.
So
you know, that's one example where in my language, you know, if I call a function with a different module, it should still be able to inline it, right?
Have you considered using link time optimization? Because that can do some interprocedural optimizations. It basically works, it combines all of the translation units into one LLVM IR file, depending on the LTO or thin LTO.
If you ask for slow linking, it can do more things.
So
I tried that, it didn't work for me.
So there's sort of 2 sides. So the optimization side is mostly, so it's like right now I don't have a specific list of optimizations, but like, oh, LLVM doesn't have that, so I'll have to do it myself. It's more the sort of thinking that if I can do as much of the work before LLVM, in theory, I can make sure that LLVM doesn't slow down as much, depending on, you know, how much code you feed it. And of course, there will be a balance. Like sometimes it makes more sense like, oh, let LLVM do this versus us. But you see with a lot of projects, they might use LLVM and they just shove like all of their code in LLVM. They're like, please optimize this for me. And then they're surprised that it takes quite a while.
I think that's a very good idea. And that's, I think it's also what explains compilation times of Rust, because I have seen the LLVM IR generated by Rust, and compared to Clang, it is not lightweight.
Right. Rust actually, they at some point a few years ago introduced a new sort of mid-level IR specifically for this problem. Because they specifically said in the middle, like, we're just shoving too much to LLVMs. We need to do some of this ourselves. And so, basically my approach is I use a sort of a dumb code generator. Like I feed it at some point reasonably optimized IR. And then I tell it, hey, maybe squeeze out some architecture specific optimizations, things like that. And that's it, right?
So
I have a long answer. Go ahead.
Would you reduce which passes you select for LLVM to run, or do you just let it run all the passes?
No, so there's one other question about link time optimization. I looked into that. Two forms. One, at my compiler level, I just squash all the IR modules into one. And two, because my generated code still links against a static library written in Rust as sort of a small runtime taking care of like scheduling and some other things. I looked into link time optimization to essentially optimize out those function calls towards that library because Rust has some support for that. The problem there is the way you do this in Rust, you compile your library or your program with a bunch of flags, and it will, I believe, include the LLVM IR in the object files. And then through link time optimization, you can treat it as if it's all one thing, basically. So it slows down your link times dramatically, but in theory, you can optimize away a lot of stuff. In practice, I've never gotten it to work reliably. In fact, I had it working once on my laptop months ago. I tried to run the exact same thing on my desktop, which I think the only some hardware difference, like different CPU or whatever, but same OS, same libraries, everything. I've never been able to get it to work. So I kind of gave up on that. It's like, maybe 5 years. But so coming back to Derek's, right now, the only LLVM pass that I'm using is the mem-to-rec pass, which is, as far as I understand, more or less required in the sense that if you don't, and you use the LLVM recommended way of sort of generating the IR, where you basically treat variables as like stack slots, you're going to get really terrible code. So that's the only pass that runs, which basically turns all these loads and stores into like registers. My long-term plan there is that I looked at the different optimization levels that LLVM has, like 0, 01, 02, etc. And I asked about it a bit in the Discord a while back. Those flags basically set which passes to run. But I decided that I'm not going to touch those flags. So I have it set to 0.
So your mic's on and your typing is loud.
So I'm going to set that, which is also what I have now, set that to 0 and then add the passes myself if I find that they're useful. And that's probably going to be quite a bit of effort because there's so many of them. How do you figure out which ones make sense? Do you have to perhaps, if you enable this one, do you also need to enable that other one? But I think it was Arthur who showed me, or Matt, I don't remember. Swift does the same thing. They basically set the LLVM optimization level to 0, and then they add their own passes based on, I guess, what they deemed necessary. And again, that's so that if you build an executable with release mode, it's not something like, oh, let's run these 20 passes, of which 15 probably don't even make sense for your language, but they still take up a considerable amount of time.
You can imagine for Swift, they want to do something with the arc reference counting, very specific. It's not common.
I have no clue. I when I initially looked at those flags, I was operating on the assumption that they were kind of geared towards Clang and thus C specific languages. And I think if you're writing like a compiler for your computer science class, your professor's like, it must be fast, and yeah, set it to 03 because you're gonna compile it twice and then never look at it again. So who cares? In this case, I just really want a bit more control, and perhaps crucially, I want to understand sort of what it's running. So I don't want to just blindly add 5 passes because some blog post told me to. I want to know what do these passes actually do? Do they make sense? What is the impact on compile times, etc.?
One suggestion I would have is to do the ablation study. It sounds fancy, but basically it tries to see how valuable something is by removing this and measuring the difference. So as a starting point, you can, for example, copy paste the O2 pass line and then start removing the passes from this one by one and seeing how much performance do you lose or gain. And the ones that do not contribute, if you don't lose any performance, that for you it wasn't important, then you have some confidence that you can remove it. That's one simple idea.
Yeah, that's sort of what I did actually. I like right now there are not really any good benchmarks to like really test these sort of code generation differences. I would expect those to be very CPU bound in general. So I use my test suite as the quote unquote benchmark. And I couldn't tell a difference between basically 00 and 03 in the runtime of it, which I suspect the big part is because the crap IR that I'm feeding it initially. But at this stage, it doesn't really matter. So my compiler currently, it does have a distinction of debug mode versus release mode, but there's no actual practical difference between it because there's no optimizations. And I might even, in the long term, take this approach of Go where there is no such flag. Like the default is a release build. And then maybe there might be a flag to like squeeze out extra performance at the cost of greatly increasing compile times. But that's something I haven't quite decided on yet, mostly because I'm not sure yet if that's going to be realistic, because I haven't written any optimization passes yet.
Are your test programs very large? Like, do they generate large output programs? Like, can you just look at the generated assembly and see this is more efficient, that's less efficient? I don't know.
That only goes so far.
Yes. So in my case, my test suite, for example, it's quote unquote large in the sense that it's an entire test suite and all of the standard library. So assuming I haven't accidentally left any dead code anywhere, because I don't have any dead code warnings yet. Basically, all code is used. So, for example, dead code removal in theory wouldn't do anything. So in that sense, it does.
We can't godbolt language.
Sorry?
I assume we can't use godbolt on your language.
I know it's not there yet. So, and I mean, I've looked at like executable sizes with things like Google's bloating bloat phase. Sorry,
still a couple weeks out.
I don't know. That might be a bit longer. I still haven't figured out how I'm going to do like an online playground either. But point being, I've looked at the code sizes, the assembly LLVM IR, and I think right now it's still in this stage where I'm just feeding it too much garbage to even consider optimizing it on the LLVM side. Like I first need to do even simple things like some basic inlining on my own IR, some basic devirtualization, things like that. Instead of LLVM, make it work, please.
Yeah, I got a long answer. If before we change the subject,
try and do something. Yeah, Levo, go.
No. It's going to be long. Derek might as well talk.
No, it's okay. It isn't that important. So go for it, Levo.
Okay, so I have noticed that LLVM is slow based on how much instructions you give it. It didn't seem like it depends on what kind of instructions you gave it. It's just
when you say slow based on the number, you mean more than linear time?
I'm not actually sure. I didn't try to measure that. I just noticed that when I fed TCC a bunch of instructions, it was fast, and Clang, it didn't care how long the lines were, or parameters, or how much. It didn't seem like it cared how much variables he had. It's just every time you gave it something to do, it was just slow. So
that the compile time grows non-linearly from the IR size. We've definitely seen these effects.
So you have not.
Do you remember
Archer,
what
you're saying-
LLVM was shooting for? I have a vague memory of them saying they wanted it to be less than square root times n as it grew.
I don't remember seeing anything specific.
Well, you do almost any register allocator on the planet, and the best you can hope for is n squared in theory that you beat the constant factor way down on.
I guess the better question is, do they actually measure it? Whether they introduce slowdowns, because I remember lots of projects that optimize the hell out of their compiler front end and middle end, and then upgraded to the new version of LLVM, and then had lots of questions why the compilation was now 30% slower. And it's because LLVM learned a few new tricks, and that came at exactly that cost.
There is a compile time tracker now, and actually, if you have a patch for review and it has significant compile time impact, there will be people who would come and tell you like, hey, your patch increases compile time by this. It's not acceptable by default.
Wow.
Oh,
Holy
that's
shit.
nice to hear.
So how do you know that, Archer?
Well, we've had a lot of patches like this.
C2, by the way, got hammered on compile times from the start. That was a known big ass issue. Every little thing we did to slow the compiler down, I got bitched at.
Are we talking about optimization builds?
Yeah. But both code quality and the time to get code. Like Java was the first to say, we're going to run the compiler at runtime. So the time to completion of your answer was the time to compile the code along with the time to actually run the code. So if your compiler was slow, it took longer to get an answer. And there were plenty of people who bitched about that. So there was an entire, I went down for years where every little thing you did to increase the compiler had to have a payback on the running time to make up for the slowdown in the compiler. And, I got bitched on that endlessly.
Yeah.
But that was probably worth it. I mean,
in the end, I think it was
pain
worth
to
it.
quit, but removed a lot of pain from every server on the planet. Practically.
Yeah, right. No. The end result was good, but I was in a new zone that no one else I knew of was in, which was if I wanted to make faster running code, I couldn't make the compiler slow down. But of course, everyone who wrote an optimized compiler slowed it down to make faster running code. That was the norm. And I got this, hammered from both sides that, as far as I can tell, no one else did. So I was like, what the hell am I doing here? Why? How do I do this?
The slowness I noticed was during debug builds. So that's why I went to TCC, because I just did not like it.
One of the fun games out of HotSpot was the debugs were, you ran optimized code, but you still debug it. But you have to spit out the debug info, and that actually takes significant time. And there was a round of optimizing how fast I can spew out debug info.
Yeah, I think I measured that at 20% of TCC's time, but I don't actually remember.
Yeah, I totally imagine that. It's a lot of high volume, bulky data. It has nothing to do with code. It's just bulky data.
Yeah. So the other thing I did for my compiler was since I wanted it did not, since LLVM wasn't optimizing between compile units. What I did was I compiled some of my C++ code into IR, and then I inject the IR into like Boolean builds. So I got cross-language inlining working just by doing that. I was kind of surprised it was working. I assume it would, but yeah, that ended up being a great win for me.
Interesting. I know the Grail project guys were doing cross-native call boundary things where they had some way to take C code that there's going to be a foreign function interface from Java and inline it into the compiler's IR.
I mostly did for a CPU intrinsics.
Yeah. There's a lot of really cheap intrinsics that you just rather not write the compiler for shave or whatever. Hey, I got a video codec here or something that's going to be quick to cross the boundary, but you just wanted to say, I'll eat your C code and then not have a call overhead to cross the boundary. That's one of the issues. The Java to native call overhead is 50 to 100 clock cycles. So if the native you're calling gets its answer in 5 clock cycles because it's computing current time nanos or whatever, you can't make a foreign call out of that. You just die the overhead.
Oh, I forgot to mention one other thing. The reason I was doing compiling it down to IR was because I had a standard library that I'm shipping, like a runtime, but there was a couple of functions I just wanted to be always inlined, or not always inlined, but inline if possible. So since that has to be in the compile units, a select set of functions, I ship an IR so it can be combined to Boolean builds to get that inlining.
I just posted something I wanted to highlight. The compiler Gym Explorer actually allows you to interactively play with selection and ordering of LLVM passes and look at the effect on the LLVM IR. So that's something you can experiment with. And given that I have implemented this entire selection framework, you can actually throw machine learning at the problem, for better or for worse.
Wait, who? I'm sorry. Who implemented this?
Oh, that's Facebook AI research.
Oh, Facebook AI. Oh, interesting. Yes. Okay.
So I have a comment about using your own optimizer before LLVM. So one of the problems with this approach is that at some point, let's say you want to do inlining or like your own devirtualization, at some point you realize that in order to do this, for example, in order to do devirtualization, it would be nice to do some other like standard optimizations, like common sub-expression elimination, GVN, something like that. So you implement this, like you want to do that code elimination, you add that. And at some point, you end up just implementing all the standard optimizations in your own optimizer before LLVM. And then LLVM would also have all of that. So that was exactly the reason why we decided against using split optimizer. And instead, we just encoded everything we needed in LLVM and like hacked LLVM, introduced our own optimizations there. So we can reuse the existing infrastructure, like all the standard optimizations are there and they just work for us.
I've seen, Arthur, what you've said, I've seen that done by other projects as well. Slippery slope. Well, we can get this inlining, but we have to discover this fact. So we have to go dead code. We have to do constant props. So we, and it builds and builds and builds. And suddenly you got an optimizer already.
Yeah, like your own LLVM before LLVM.
Yes. I wonder how far Scala goes down that path, for instance. I know they do a lot of stuff to try to specialize ints and things.
Did you actually write a backend optimizer, and how long does it take to learn the code base?
Who are you asking?
Arthur.
So we are using LLVM as a JIT compiler for Java as well. And we have a whole team, and this effort has been like running since 2014.
So quite a few years, yeah.
Yeah, so it is I think unlike many other cases where people try to use LLVM as a JIT or as a backend, we invested much more effort into this. And I think that's why we're probably one of few, if not the only, production user of LLVM as a JIT compiler.
The Julia guys try to use it as a JIT compiler, but they, at least a year ago, the code quality really sucked for not having the right integration between the runtime and the backend. There's an effort there that you've done that they have not.
Yeah, I think in short, it is doable. It takes effort, but yeah, if you spend as much effort, well, you'll get great results.
So you guys have written a handful of, like, have you written passes, or is this sort of a layer that's not really fitting into the pass framework that's sort of somehow integrated with LLVM?
So yeah, overall, we have our downstream fork. We follow top of tree closely. We have probably like, I don't know, dozen, 2 dozen of our downstream passes. We also have some tweaks here and there in the common code. Usually it's ideally we would love to upstream everything. It just takes extra work to convince community to like generalize our optimizations so they are applicable in general for and interesting for the community overall. B, it just takes longer to like get things reviewed upstream. So that is why we have our downstream code. But there is nothing to hide. In the ideal world, upstream everything.
But you have to fork LLVM to do that.
Yeah, we have our downstream fork.
Like I understood that you brought the profiling data from the VM into LLVM, which I would have thought would have been a major effort.
Actually, there is everything in LLVM upstream to encode profiling data in the IR. Like you can encode it on like metadata on branches, things like that. So there are analyses that would compute block frequency info based on this information. So this part actually, like we had to improve things here and there because I think in upstream it is used only with PGO, and it's not the most commonly used configuration. So we had to fix things in different places, but overall it was there before. The most work we had to do, and it was in the beginning of the project, it was interaction with GC, like save points and state points, how to communicate this information with runtime, and then encoding of metadata for de-optimizations, for example. So this was also some like extension to the IR that we had to contribute upstream. It's via operand bundles. And then in terms of optimizations, like there was a lot of work done around range checks and like scalar evolution analysis. Just we have so many of them, and that's less common, I guess, in the code that Clang usually goes.
Yeah, I can see range checks not being there, but I would have thought scalar analysis for like ranges and enums and the like would have been pretty common.
Well, I would say it was there. It's just we had to make a lot of improvements in different places, just because we saw cases that were not seen before in Clang, or no one.
Yeah. I mean, when I was doing C2 at Sun, all the compiler technology was C code. Everyone had, this is how you compile C code well. Well, I saw all kinds of stuff that was not C code. Didn't look like it, didn't act like it, like the range checks and like the null pointer checks. No C compiler just touched those. So that was all new for me then too.
Yeah.
It gets it.
So is it very hard to, like, has it been a lot of effort to create and maintain your own passes in LLVM? Like, I haven't encountered many people who have actually ever written any, to be honest.
And you asked about LLVM passes, right?
Yeah. And it's also interesting because, you know, we're talking earlier about all these people who are saying, well, you know, I have to optimize my code before I get into LLVM, like reduce the IR, whatever. Like, shouldn't the natural thing be to just create an LLVM pass that does that? You give it the naive IR and then you run your own pass that sort of does your cleanup in LLVM. Like, so why is that not the default thing? That's confusing to me.
Yeah, that's what I was advocating for, and I was saying if you are doing the split optimizer approach where you have your own like optimizer before, you will end up re-implementing a lot of things. So what I am advocating for is it might be better to implement your optimizations in LLVM, like have your in your downstream fork, or maybe try to convince upstream community to have these passes that would do what you want. And I think like making a pass, it's a pretty straightforward thing. The only thing to like worry about is if you keep it downstream, as was mentioned before, APIs are not stable. So if you choose to live with stable releases, then switching between releases will be a pain. Like it won't happen often, but once you need to change, yeah, you'll need to like probably fix things. We do it differently. We just follow the top of tree, and we constantly merge new changes, and we just update things as they change.
How much effort is that? You burning a person full time at it, or?
Not full time, but we have a person, like we have rotation in the team, and we have one person who keeps an eye on it. And it depends. Sometimes like it's just few days without any issues, automatic merge just does the job. Sometimes you can encounter some like problem, especially if it's some like semantic change, like you see tests started failing, it can take a few days of your time just to figure out what happened.
But you're staying on top of it.
Yeah.
So the diffs, the semantic changes are probably relatively easier. Okay, that was the question. It's like you're burning a full-time engineer, kind of, sort of, not really. That's what I hear.
Not really. Yeah, not really.
Okay, interesting.
Oh, when I was trying to optimize my runtime and a little bit in my compiler, I noticed that Clang easily gets confused and will not optimize certain things it should be optimizing. So I found that just giving LLVM very clean IR goes like a long way, because it's really easy to have a corner case or to do something slightly funny that just confuses optimizer.
That, by the way, works for everybody. You're right. Simple, clean code. In Java, C, or whatever, you get simple, clean IR, optimizer cleans it up.
Yeah, and people optimizers need things to follow patterns. So when you're not clean, it means you're not pattern.
You're not the pattern that they're looking for. Yeah, these are not the patterns you're looking for.
When I say clean, I mean you don't give IR and just be like, yeah, the optimizer would just take care of this. Like I had to take care of everything so it doesn't accidentally produce junk code, especially with aliasing and all that.
If you have semantics that are not cleanly translating to the IR that the compiler expects semantics, then he can lose like all aliasing information. As a, for instance, hey, I have Boolean objects, they don't map to C objects, so Boolean structs aren't C structs. So the compiler says, I got a bunch of random accesses to memory, they all alias to each other because I don't know nothing about them. And then suddenly you get no optimization across these things. I mean, that can happen. I'm not saying that's happened to you, but that's a thing if you can't get a clean translation to the compiler's IR, including the semantic level.
There is a document, something like recommendations for front-end authors or developers that describe how to encode common patterns in LLVM. Once I find it, I'll post the link.
I'd say, yeah, if you got a link, that'd be cool. I'd be curious, because that tells you something about what LLVM is expecting to see and what he's willing to optimize on. Yeah. Wow, we got 20 seconds of silence here. Wow. We beat this topic to death? Cannot have imagined that we had beaten it to death. All right, I was going to do an AA update. That would be a big change from LLVM and head into the land of type theory things. Do you want to go that way, or you want to LLVM? I see a couple of head nods, yes, but I only see like 5 people right now.
So I added the link to that performance tips document into Google Doc. So it's number 6 in the list.
I got to find it now. I've opened up too many windows. So I cannot find my normal stuff here. And I want the better version. This guy. Okay, let me see if I can do this. Come here, you share screen, Google Docs. I'm going to share Google Docs. This is AA. So I've been doing other things this week, a bunch of them all over the map. So less AA progress than maybe we would have liked, but I also sorted out a hard problem for me. Let me look at this and decide which piece to go with here. Yeah, we can simplify this guy a little more here. So I have a simple program in AA. This is not the one. Where's the one I want? FX, oh shit, I had a simpler one. Let me take a second, find even simpler one because that will help even more. I want this. And I'm just going to do math land there. I think this one might be better. Where did you, Google, what did you do? There it is. Jeez. Man, what I want to do here, and I want to do, we'll put math in here, so one less thing. Okay, so what is the type of this function? Let me add some indentation to help Cameron sort out what it is he's looking at. I'm being mean to you, Cameron. Let's see. Ooh, that's kind of ugly. How about this? Is that better? I don't know if that's better or not. So all I'm doing here is I'm counting down X, and then I'm reporting, and then I'm.
Leaf, could you increase the font size? Because on
Oh.
a laptop screen, this is tiny. Just
Right.
the entire screen font size.
Okay, so that would be go to Google Docs and
You have this 100%. Maybe you can change it to like 200.
for the
Need the
doc.
header.
Good.
It's on top. Oh, that's better. Much better already. Yeah. Thanks.
Okay. Yeah, right. Fine. So there's probably a simpler function I can get in here yet. Oh, I put fun in here. I actually have to have fun in here. This.
Yeah.
Quit. Oh, somebody wrote it for me. Thank you. Blah blah blah. And then fun is the thing. Okay. So all it's doing here is it's like doing a factorial, except it does a do nothing. It counts down and applies FX. I can actually get rid of the FX apply and still have the same issue. It arbitrarily counts down. There's a couple variations on the same theme here. Let me see if I can simplify this one some more and get it more like I don't think I need FX here to make the issue show up. So randomly return the current value of X or call yourself recursively X minus 1. Okay, what is the type of this function? It's a function which takes an X and returns either an X or the result of the function, which means it's returning an X. Okay, what's the type of X? Anyone want to volunteer a type for X?
It tries to be int because here you have to perform math with it.
Yeah, so it's AA. Everybody can have an operator, and all things allow operators. So X is not bound to be an int.
Isn't it just an object that has a subtract operator?
Yeah, it has a subtract, takes an int, returns an int. So it's an operator who it is an object.
No. It has a subtract that takes an int and returns something.
Yeah.
Mm-hmm.
Yes, you're getting closer now. So it's assigned a type, which is some generic thing that has a superclass, which I'm not going to put the content in here. A superclass chain. Somewhere up the superclass chain, there you find an equals operator, which there are other fields that I don't know anything about. The superclass operator itself is, like all operators, is a overloaded function body, whatever. It's an overloaded list of choices for the operator minus. One of the choices, and then that will all be functions. One of the choices takes whatever type X is and the int type and returns me another X because fun returns an X. So the operator has to return an X. So for instance, it would be legal to call fun with 3. This is legal and return some number less than 3. How many times you call math ran? But I could call with fun of 3.14. That's also legal because floating point returns minus an int returns a float. But I could also put in here some matrix that happens to have minus an int and returns a new matrix. So what I didn't understand was I can't define what the overloaded choice for the operator minus was here until I realized I was actually going to return it from fun, and he's going to support all these other types. So at any given context, I have to support an operator minus it is anything that supports an operator minus somewhere up a class superchain list, which I'm not showing, that takes an int as a second argument, returns yourself as the first argument, is a valid thing. And that was what I diagnosed sometime earlier in the week. And sorted out. I think that was sort of the last weird case that I was fighting through, excuse me, in my porting over to AA. Like, I think I've now poked all things like and or and short form or whatever, short-circuiting operations, and I've done stores and functional stores. I guess I'm maybe not yet done closure things, not very much. I've done closure things earlier. I haven't checked closures in a while, but I'm kind of running out of things I can break myself on. But yes. Okay, so somebody wrote like a Haskell version. A fun takes an A and return. I don't know how to read the thing. Returns me something -1. It's minus an int, not -1.
Okay, so its function, it takes an A and produces an A, and then it has the constraint that if you subtract 1 from the A, then you get an A back.
Okay, what language did you type that in? Is that Haskell or something?
I think you try to
Strauss
do something like it in liquid Haskell, but I don't know if it's the right.
I would contend that there's no guarantee that the x -1 needs to return at something typed x.
Yeah.
For instance, I could have a floating. I could have I could have a string which I've arbitrarily added a minus to that takes the length of the string and does the length of the string -1, and now it's still going to work in this function. But
no. As soon as you call length, the x is converted to an int. As soon as it's called length.
No, but I'm saying that this minus operator on my weird string.
Yeah, and what happens to you then, Derek, is that the recursive call to function is either past a string or past an int. String and int.
I think what Derek is saying is it's not necessarily a recursive call. It could be a call to a different fun that takes a string.
Yeah, I'm just saying
the fun that's
assumption that it returns an x is not really necessarily encoded in this function. That the result of x -1 doesn't have to be typed x.
It does for this function, not in general. Like operator minus can certainly do string -1 returns an int. That's fine for operator minus. However, in this function, the inner word fun must hit on the function that's the let defined ahead of you. It's let rec outside of you. That is the definition for fun there. This function, that means the value that fun returns will be used as an argument to fun.
Yeah, but wouldn't your type system determine that doesn't have to be an actual x as the return, that it can be an x? Or it can be
it's going
something.
It has to be both an x and also whatever fun returns, which is only ever an x.
Yeah, that's right. Except for the inner call to fun could be called with a different type of x. So you have it
can't because you
get kind of locked into one.
The term is bound into the function.
It's bound into the function. Yeah, we could write the program that would allow what you're talking about, but that is not this program.
My question would be why Hindley-Milner doesn't go all the way to an int. Instead, it decides it's a structural type.
Right. The normal Hindley-Milner says the operator minus is a special primitive in the language that takes int and int and returns an int. That is not how operator minus works for me. For me, operator minus is an expansion. I load from the class to the left-hand side, which yourself, or if you're primitive, the int class or float class, an operator. That's the first structure field lookup right there. Then that returns me a tuple, which I do operator overloading on. There's no overloading happening here, so there's only one tuple member. And then you pull a function out, and the function gets past the first argument and the second argument and returns anything it wants. That would be Derek's solution of string int returns an int. That would be fine for the operator expansion. In the context of this test case, the second x there, or in my inner type, is bound to be the first type because of the recursive, and therefore it has to be return an x again. but I'm not bound to be an int. I'm bound to be somebody who supports an operator minus, who takes an int as a second argument and returns the first guy. Here it's an X again.
Of course, that would allow more types to qualify for this function. Anything that has a minus, that has defined a minus, as you said, an int, a float, a matrix that has defined it on minus. Yeah. So this is
right.
Yeah. This is going for the operator route, not the type route. Anything.
The operator, right? The operator is just a syntactic expansion. So I can replace the syntactic sugar in line with a new copy of fun where I've expanded it manually. Where instead of saying x minus 1, I say x does a field lookup of the minus operator, which does an unresolved field lookup, which I'll resolve to 0. That's the function. That function I'm now going to apply arguments to. The arguments are x and then the 1. So that's the expansion I'm looking at here. And then the funny name for the field lookup is just because the operator is involved. And then the .0 is because I did field name resolution for overloading. There's no overloading going on here, so it was a trivial resolution. Turns out that's actually not in general trivial, and I have to do a comma ... because I might have many other operator choices for -1 or x minus. So I do have to do a field resolution there. And then the other half. Well, go ahead. Somebody go ahead.
Yeah. So I'm thinking of like a variation of this, which so sometimes a pattern that I often use is I'll have a function where it takes an optional map of options, of like settings or whatever, and some piece of data as a second argument. But I would often have a version of it where I can just pass in, or say, actually, let me change this. I could have a version of a function which takes like a piece of data or a map, which includes some settings, and a piece of data is somewhere in that map. So then I have 2 different signatures of this function, but they're both one argument. And then I could call it with just the piece of data. It'll construct the map of default stuff and then call itself again with the changed type. And so that seems kind of like what I was saying here, like imagine that X is string or whatever. And so but it's a more like legit scenario. And so I was just kind of curious, like how can, it's still a bit of it seems a bit contrived, but I think that, I think.
Well, so what I heard you say is I've overloaded function fields based on type arguments. And
like normally what I would do is, because I'm dealing with a not strongly typed language, then in these types of cases, if they occasionally happen, I just like kind of query the data, like, is it a map? Is it the thing that I want? And I just do whatever thing, and it gets called regardless. But here it's strongly typed, so I guess
you can choose only one type.
Resolve something, right?
Yeah.
So is it just, maybe that's just something you can't do or shouldn't do?
Right. Well, there's another way to do that in these languages, but you come out of a different direction. Generically, you could always take a very weak argument X and then do an instance of test inside. Hey, you're an instance of a map, do this. Else you're an instance of a that, else throw an error.
Yeah.
Life goes on.
Yeah. Okay. So you could still do that.
I could do it directly the way you said, right? There's another version that you get out of C languages where C takes arguments for X, for int and for string and for float, and you get different function calls. And in the generic code I wrote, I didn't supply a set of functions that took different arguments per se. So it's the same function every time, and therefore it has to be the same argument passed in every time. And somebody says something about operator precedence. By the way, how I'm doing, not precedence, how I'm doing widening is with these primitives where the overload resolution does the widening, because you pick a float, int, subtract, returns a float instead of an int, and that's the widening operator. It's tied to the overload resolution as opposed to being tied to something in the language that does widening. Precedence, that parser does precedence. It's Matt saying, old idea for operator precedence. I'll have to look at it, Matt.
Maybe don't take it very seriously.
Oh, okay. Oh, I shouldn't look at it seriously. I see. Well, you know, in the land of C, there are like 17 operator precedence levels or something. There's a lot. So you know, my parser just has a list of them, and operators go in the list wherever they want to go, and then I sort the list when I start up, and that's the precedence I'm using to parse this file. And it doesn't get to change in the middle of things. Whereas operators can just be added and removed, and that'll just happen because it's just field lookups.
Have any of you changed the precedence order?
I'm sorry, what now?
Vis-a-vis what language?
Well, most languages just copy what C did. I was just wondering if you guys changed that.
Yeah, C's broken and Java copied it, and Java's broken. So yeah, we changed it.
Right. Like the instance of in
too.
Java binds the wrong way. You can't do a not instance of without wrapping parens around it.
For example.
For example, yeah, that's one of them. I also am in agreement with a bunch of folks that mixing and or in the same expression, at least for me, it looks a little confusing. You forget which order they bind, how tightly they bind, and I might want to demand that you parenthesize if you're mixing and an or so they don't.
I did that as well.
Okay.
What do you think about raising the left and right shifts above multiplication?
Oh, shifts and multiplies and shifts and adds. I haven't thought about it. I know that I fight shifts and adds and shifts and multiplies all the time because, you know, it's a compiler, you do shifts instead of multiplies because that was the thing back in the day. So I know it's an issue, and I'll look at it when the time comes around.
If you use function calls for shifts, you never have to worry about it, right?
Yes, but then you have more parens than you care for. In normal everyday coding, I don't use shifts very often, and a function call would be fine. I'm writing my linear congruential random number generator. I got shifts like freaking all over the map, and I'm kind of like, I don't really want to say math.shift or binary.shift or whatever it's going to be. I'm just going to put the shift in.
Also, sometimes you just need to shift left C out by hello world.
Goodness
Well,
gracious.
that's a different
Please
one.
no. Please no.
That's right. That's using shift operators.
We dropped all the bitwise operators into one bucket, and it's below lower precedence than additive.
Okay, so you right.
Why is that?
Yeah.
Because it generally is perfect.
Yeah. It might be. I haven't tried that one, but you changed that operator sequence. Yeah.
Well, we analyzed both Java code and then the ecstasy code that we had written already, and we found that these were kind of the natural orders as implied by code that exists. So
Right. Right. I mean, when I get to shifts in other code other than what I'm doing to do machine code, really,
right.
The shifts are, I mean, it shows up in hash functions, and I don't know, not many other places, a handful. There's a very specific thing here. Let me go do.
I just meant all operators have the same precedence, like they're left associative, so you don't have to even think about it.
Oh, yeah. Well, compared to add.
Okay, so I have the mathematical operators all have the same precedence. I believe, and I have to say correctly, and an or are higher. So if you do like A plus B and C plus whatever, they're like separate. So then it's like A plus and the others.
Oh, here's the operator table thrown in.
So if some things have the same precedence, do you require parentheses or?
I don't require it. Like there's no compiler warning if you don't. But I found at least for like the, let's say the logical operators, you know, shifting, addition, whatever.
And well, I threw down a rotation for a hash function, and then
Yeah,
I put parens wrapped all through it.
Yeah, so what I found is if you use the same precedence for all normal, so all, let's say all mathematical operators, so shifts, additions, whatever.
Yeah.
Occasionally you might have to like, oh yeah, wait, because we're not having this weird precedence rule, this we now need to wrap in parentheses. That is mostly if you have things where you want to do like so quick like a divided by b plus c, but you want it to evaluate as a divided by b plus c, not a divided by b and then add c. So for the most part it works fine. I think occasionally you have to like remember like, oh wait, I'm translating this C code where they rely on this particular precedent. So
mathematically, I think multiply ahead of addition for me, that one just seems straightforward. But the other bit operators, ands, ors, shifts, max, hat, whatever.
Yes. So what all math bonds have the same, and then and or they're like higher, so you can still write your operators and ands or as you would expect, and that's basically it.
I wrote my or higher precedence than and. What do you guys think?
Oh, you put a precedence between and bitwise and an or. That's the mathematical one, or bitwise and is a conceptually modulo.
Wait, Levo, did you just say that you do ors at a higher precedence than ands?
That's backwards, yeah.
So I mean,
Yes.
the challenge with that is that's like saying, well, I mean, that's one of those learned things that will bite hard just because everyone has coded in C, C++,
Well,
Java, C#, whatever. They all have the same precedence, and you're kind of going opposite. You're not just shifting, you're reversing.
If you look at the mathematical flavor, so this is Boolean, capital B Boolean algebra and De Morgan's laws and the like. The normal semantic is that the multiply operator on the group is binding tighter than the add operator, and the and operator matches to the multiply on the Boolean group, and the or is the add version. So you're kind of fighting the mathematical world there.
Okay, so in my real code, in my compiler, what I do is I have variable and then I or a bunch of flags together.
Yeah.
So for me, I prefer to have all my flags or together and then do the and.
Yeah.
So that's the way that's why I did higher precedence, but I don't see a reason why I should be anding and then doing the or, because that seems like you would want to put a parenthesis around that.
Well, that's what I'm saying is that there is a 100-year history of Boolean algebra doing group mappings to, or maybe integers mapping to the same group as the Boolean algebra is mapped to, and then and multiply operators, which an and is, are ahead of or bind tighter than ors, and that's the reason there's a semantic that way, and then you have to throw down parens when you don't follow that. So just saying you're adding a confusion of some kind there. So C actually does equality lower than relational. Like if I do A less than B equal C less than D, there's a definite order there. Maybe that makes sense. Okay. Like I'm still surprised at the order of these things.
Well, that's not C. That's that table is ecstasy.
Oh, that's ecstasy. Oh, I see. Okay, fine. Oh, I should have recognized .new and been like, I thought I said maybe it's a C++. Yeah. No.
So I see you reduced it a bit, I guess.
Yeah, he's only got 12, 15, down from 17.
I think at the last time I complained, you were like at 25 or something.
No, I don't think it's changed.
Oh, really? Okay.
Yeah.
I thought you had more in the past.
Oh, you got pre-increment operators, and their precedence is same for whether unary. So, oh, unary plus is in there too. Yep. Okay.
Yeah. So basically the post are slightly higher than the pre.
Okay, so if I do plus A plus, which I should be shot for doing.
Yes.
But there's a well-defined order, but not necessarily the order I'm expecting.
Correct.
The real problem there is I shouldn't be expecting an order in that, and I should be shot instead. Fine.
I think one thought I have to the thing Yorick described, or like the small talk way of doing things. I think regardless of the ways, whether you're like having no precedence or having some different precedence, I think there is like cost of being different, which is like fine if that's like the choice we made it and it's fine. But what I am personally scared is the cost of reading code without parentheses and then having to question myself each time, okay, is there no parenthesis there because I really intended it to be this way, or because I fell back to old assumptions about how precedence works and I really need to fix that code. That's a bit, I can't really predict how much of a hassle it
Simon is a natural Lisp programmer.
It prints everywhere. Everything's a paren.
Yeah.
Yes. A paren for every operator and an operator for every paren or something. Yes. No questions. Just can't read it. No, lots of spurious parentheses.
No, I kind of agree there in the sense that, yeah, I'm kind of toothing my own horn here. It's a little easier if all operators have the same precedence. You know, of course, if you're not familiar to that, you're like it takes some adjusting. And I sometimes find myself like looking at it like, well, oh no, wait, yeah, I made it all the same precedence.
I actually disagree that having them all the same precedence is clearer. I think that if you dislike operator precedence, you should just not allow a chained set of operators and you just force the parentheses.
Yeah, there are obviously arguments for both sides. I like the idea of requiring parentheses when you have these sort of operator chains, when it's like, you know, A plus B divided by times blah, then it might be nice. I don't quite know how you would reliably detect that and not give false positives for simple cases, right? At a parsing level, you could probably say like, oh, if we have the expression A op B, then it also must be surrounded in parentheses. But then you end up with having to write like, if you do like assign A to A plus B, requiring parentheses around that is kind of ridiculous, right? So you end up with this, I think, reasonably complex logic where you start looking at these operator expressions.
But you basically, if you're saying that operators have the same parentheses, same precedence, if you say A equals B plus C, doesn't A become B, and that B plus C is just off in the void?
Well, it'd be if the assignment operator has same. Oh, that would be ugly.
Yeah, so if you do A equals B plus whatever, it evaluates as A equals B plus whatever. But first of all, that expression makes no sense because you're doing a Boolean result with an addition. Like, how are you going to add Boolean 3 to 4?
I was saying assignment. Yeah.
But my goal was to add two numbers.
Right. Okay. So assignment is a different story. Assignment I do not treat as a like an operator. So if I do, you know, as A is not equals A is 10 plus 5, it is not A is 10 plus 5 on the result. Like it's A is the rest.
So you're taking assignment out of the operator.
Yeah, I mean because they're not operators.
Yeah. Okay. Yeah.
Right.
It makes sense. It's just,
I did too. I have assignment is not an operator.
Right.
Yeah.
I think at the end of the day, like the whole operator precedence, I think to a lot of people who people are used to certain precedents because at some point some Greek person, 5 million years ago, whatever it was, decided, oh, the operator precedence has to be different because I don't know why reasons.
Why binds more tightly than add.
Right, and we stuck with that for whatever reason.
Yeah. There's a history there that we could go look up and figure out where.
I mean, it's very similar but slightly off-topic one. A lot of shoes are pointy. There's no reason for that. Somebody at some point made that decision, and we stuck with it. Now I can go on for hours how stupid that is, but I won't.
My shoes are not so pointy.
The toe boxes usually are. But so that's a similar thing where it is because it is, not because somebody
haven't seen
came
my
down
toes.
from the mountain and he said, I looked in my crystal ball and
Yeah,
this is the best way of doing it.
Quad E's shoes. So my toe box is this wide, but it just, it's.
Right. But so, in other words, if you're used to operator precedence, having a different precedence or not having precedence, it's quite confusing. But if, for example, if you've never programmed before and you start learning, it doesn't matter. Like whatever you learn first, that's what you pick up.
I claim there's still the hook to mathematics here. So you have to go retrain, 1,000 years of mathematicians if you're going to change that. And that's going to be too much overhead. Same as we count to base 10 because we have 10 fingers, or, I hate to pull out other ones, but there's an overhead cost for trying to rewrite the entire human population of what it means to do mathematical precedence for at least add and multiply.
I'll still stick to with what I did with the ORs. Okay. I put in a quick code example. I do this for variables. I don't typically do an addition, but the reason why I have shifts higher than addition is so I can write the variables like this.
There. Yeah, PowerShip 2 for doing aligned big allocations and the like. I did an H2O as well as C2. That one came around a lot. And then you had to print it. Well, I had to print mine because of precedence.
I don't know why, who would prefer for bit shifts to be lower precedence than adds. Like, I don't know what the use case is. I'm sure there is, but this is my use case for having it higher.
Yes, and I'll agree with you on this one.
Why would you do bit shifts? They're not faster than a multiply.
No, because conceptually, I want a bit thing. I'm not doing a 2 to the n power thing. I'm doing a 2 to the n power thing, and that's a little harder to read for me, at least. I do these bit things. It happens all the time. I need aligned masks for whatever reason. I'm making a mask. I do bit shifts because that's how
I do bit shifts all the time too for shifting around bits. In this case, I would just say 3b plus 256 or 2m. Either one works.
You have a shortcut for the million operator though.
Yeah, I don't have a shortcut for a million kilobytes or billion, but that's how I write my billions and millions.
Actually, it's G, not B, but who's counting? 3G plus 256.
Let me share the doc again here.
Ooh, I made it. Your example in Scala.
Okay, right. So this, in this case here, like, I approve of this kind of thing in the sense that it makes sense. I do this kind of thing. Usually I'm doing a -1 because I'm doing the full mask. 1 left 30 -1 to get a bit mask. And the goal is to make a bit mask. I'm screwing around with bits for whatever reason I'm screwing with bits for. And I could imagine doing 2 hat 30 to get the same effect, but that just looks uglier in my head. And Cameron's point is this is all going to turn into, going to turn into the right bit mask in the machine code no matter what you do. And his other point was that you can just multiply. That's 1 clock anyhow. It's not quite, but it's close.
Well, it's actually two completing every clock cycle per hardware thread.
Multiplies?
So it's a half a cycle.
Well, the question is it burn more resources than a shift when you get lots of them going at once, like my giant piles of Zors and Rots?
No, I hear you.
Right, I don't know if multiply is limited to 2 versus shifts be limited to 4 or not, or whatever. That one I don't know right now.
Would you guys burn someone at the stake if they did 2? I forget what the exclusive OR operator is, but if you had 2 of those to mean power of, would you just burn the person who implemented that?
Power operator.
Yeah, I don't want to implement that, but it just popped in my head.
Yeah, I've seen it as star. I've seen it as caret.
Yeah, I've seen it as 1 caret, and I've seen it as star, right?
Star makes more sense to me.
Yeah, and I will probably, for the sake of the least confusion for the universe, I will probably go with whatever Sue does here for that operator, which will probably be
C doesn't do it because ** could be dereferencing.
Could be derefs instead. Well, then I don't like the hash. Like I do XORs specifically for like hash functions and almost nowhere else. So I probably will pull XOR off the default operator pile. That's too rare from even me as an operator. And that goes with Cameron saying it'll be a bit XOR and it'll be, you know, well, I think an operator on the bits and it has to do this, and then it's not necessarily what you want. That would be ugly. That would be technically correct for AA and ugly. Oh, probably you might do. I'd make you, oh, if you want to use a lot, you would just assign it. Whoops, come back here. Okay, and now in the code below the assignment, you get to have this going on. That's not right, but it's close.
So I just wanted to extol the virtues of Lisp, you know, I mean, you don't have to decide precedence, you don't have to decide operator weird symbols, you just, you know, write out long name, exponentiate, and then you're
right.
You know,
You just put parens everywhere. Yeah,
right.
I find that harder to read though. There's some argument here for doing something easy.
Well, I mean, like one way to design a language is to say, first I'm going to use Lisp, and then I'm going to see what patterns are really verbose, and then I'm going to make those have
Whoever Anonymous Tiger is, they're having fun with parens. This would be Cameron being snarky. That's my guess. Oh no, but Alan's now laughing at me. So you gonna balance those, Alan?
No, that's, I mean, like honestly, there's this paper, it's called like indentation syntax for Lisp, and it's like how to not use parens but still write things that are morally equivalent to Lisp.
You know, indentation, the correct
You're talking about
indentation
Python now.
for Lisp is to use Emacs Lisp mode.
Exactly.
Yeah. I claim.
And I don't know about you guys, but I have seen parentheses in other languages. Just throwing that out there.
Wait, I thought your closure. I thought they had other things than parentheses. I thought they had like
I got square brackets, but and actually do a lot of just. So one of the things in old school Lisp is that every time you have a pair, like you have a binding pair, they put another set of parentheses around this. But like if you say I'm binding a let binding and I've got 10 variables, it's pretty obvious that you're working in pairs and you can just omit the parentheses. And so that's how closure works. It's kind of nice. It keeps things a little more under control.
All right. I think we're well into the realm of having snarky fun with friends, and it's 2 hours in, so maybe we should declare victory.
I wouldn't mind showing a little update. I've got kind of little visualizer thing that I got going.
Keep it under 10 minutes here.
Oh, for sure. Yeah, it's definitely under 10 minutes.
Sharing's on.
Sharing's on. Okay, let me just pull it up here. Yeah. Okay, so share my screen. I'll just share the whole thing. Okay, so I'm now I've got some small program that I run, that I compile, and I've got my register allocation for my PE array working, and I built this little visualizer ages ago that shows, because I have this like massive SIMD, and so you've got 512 potentially instances of a like a computation happening at the same time, and data could be like moving between processing elements. It can be very confusing. So I created this thing, and it's a bit rough right now, so I have to sort of toggle it with the slider, but I set up a program with an initial state, and I can sort of step through and watch it run. And as it runs, you can sort of see what's happening in the PE array. It's at the bottom, and what data is changing at the top. And it's kind of fun. It's like a way of debugging these like complex SIMD programs.
Oh, this is execution as opposed to compilation.
Yeah, so this is execution. So I've got a program here, which is so basically I'm running. I'm not sure if all this stuff is blocked.
Yeah, I can see.
So I'm running this little program. It compiles. It's basically calling this. That's this. It's got these things sort of get inlined into it, and it gets sort of. This ends up compiling down to just a small amount of code, and then it sort of figures out the register allocation both for the PE array and the controller. And then here you see it basically, you know, it has to sort of create registers before it uses them. So it creates a set of 4 registers. You can see them sort of go darker here, meaning they're available. Loads, and a load from SRAM takes a few cycles, so then it loads data into them. Actually, it goes into here, and then you know, it starts moving things around. It does a multiply, accumulate, and all this. Anyway, it doesn't matter, but I'm kind of proud of this, and I'm very happy to say that like this is my compiler doing real sample programs, sort of end to end, with all the little pieces falling into place.
Yeah, cool. So someday this shows up on a piece of hardware near you.
Yeah, I mean, I'm gonna have to go to slightly bigger programs, and I still have to get a few things working. But overall, like I've got a working end-to-end flow again after many months of messing around.
Nice, nice.
Yeah. So, yeah.
Okay. Anyone else?
That's my update.
Thank you, sir. It looks good. Yeah, the graphics thing is fun. I tried many C2 graphics things and found them fun to look at. They're probably good teaching tools, but they were never helpful for me in debugging my production bug problems.
Yeah, so I spent a bit of time in the past week getting my metadata back up to snuff. So I'm at the point now where all of the forms that after the dependency resolution and all the initial nanopass stuff is done, every form has its original source line of code and snippet of that source and stuff.
Yeah.
And I create nodes in the graph as like, I call them path nodes, and I link them to my nodes. And then when the optimizer runs, it forgets the connection to all of them, and I lose all of that information. So the next thing is maintaining those.
The debug info through the,
Yeah, so, and yeah, I don't know if that's the right approach. It seemed intuitively like it would work. That like, if I'm say optimizing code, or changing things, I just basically take all the path nodes that are connected to everything that I'm doing and attach them to at least some node in the resulting
I am doing something kind of similar to AA. I have a pointer into the program at every node that showed where I came from out of the parser. And I'm not doing anything clever if I do like value numbering, common sub expression, and combine 2 nodes. I don't actually combine their 2 program points. But everybody has some point where you got responsibly put in from the parser. And then if you survived all the way out to the back end, you had that data, and that was how I could tell where you came from. Something about it,
yeah. So I wasn't sure if how much that problem that was going to be. My thinking was that I could just live with multiple code points pointing to the same node. And then try and figure out at runtime, I'm in this function, it must be this one, not that one, or something. I don't know if that'll work.
Well, what's the data for? Is it just a?
Well, I'd like to be able to, as I'm stepping through code or sort of visualizing it in this thing, show which line of source code is actually it's tied to, and registers are just registers, give them variable names.
Yes, this is a debugging, but there's an optimizing debugging thing when the compiler fails to vectorize and somebody was darn certain it was going to vectorize and they're depending on it for performance, it must vectorize. Why did it not vectorize? And you have some feed the answer back uphill through the optimizer. You failed to optimize or vectorize because whatever, something happened. I didn't like what you did.
That's even a higher level thing that I haven't thought about. I don't know.
Yeah, the supercomputer guys with running vectorizable hardware have been fighting this fight forever and a day. How you tell a programmer why the optimizer didn't put your code on the on the super part. It ran on the serial part, but not the super part. Yeah.
I came up with a Scala equivalent on your code, but
Yeah, I kind of want to make some suggestions on to the user when they use my compiler. I want to. I don't know how I'm going to do it, but
It's not an easy problem. That's a hard one. The power steering for the end user is what I call it, but it's how do you you did something magical in the compiler, you got an answer. The user doesn't like your answer, how do you go backwards from why it was bad to back to the user and saying, error messages, performance error messages are harder. When you got something ready to show, we'll all be looking at it. All right, now I'm going to call it and go get my lunch. It's fun. We had a good conversation today. This was like a good one. All right, till we meet again.
And I got to write a lot of Lisp.
Yes. Okay. Bye-bye.
bye.